My last video was a general introduction about ANSYS Workbench. In this video I will show you how you could prepare a model, apply relevant boundary conditions, change the geometry if necessary, and analyze it in ANSYS. I have selected a 4mm Allen key for this case study. I have it open in Autodesk Inventor. Using the procedure I explained in my last video, I currently have opened its geometry in ANSYS. I have made some changes to its geometry that when it comes to the right time I will explain why and how I did them. Okay, we just browse through the geometry. This is it. This is the long sleeve, and we got the shorter arm. In this video I will assume that we will insert this shorter arm into the bolt slot, and we will use the longer arm to twist Allen key. Well, I have already assumed that this is made of structural steel. I will now show you how you can change the values of mechanical properties if you want to. So if I go back to my workbench environment, I will edit my engineering data. Now we have structural steel present. In isotropic elasticity material data, you've got the Young's modulus. If I say change it to megapascal, yeah, it shows that it's 200,000 megapascal. Say I want to change it to 210,000. Now by double clicking on that number, I can make it editable, so I just input 210,000, and by pressing enter that will be registered. Now in tensile strength, if I change it to megapascal, it's currently 250. Say I want to increase it to 350. Again I can double click and make it 350, enter. You can change all of these properties by doing the same process. Just as a case study, let's imagine that we want to see how it would behave if it was made of aluminium. To do that, go to engineering data sources, click on general material. In this table it will give you a list of common material. Aluminium is the second one from top. Press on the plus sign to add it to your library. By clicking on engineering data sources again, you will go back to the editable environment. So I will click on aluminium alloy. Let's say I'm going to agree to its material data. I'm not going to change it. It's 71,000 megapascal for Young's modulus. Let's keep it there. We go back and I will update my project with the new materials. Let's go back to our model. As you can see, aluminium alloy is added to my material list as well. Next thing is to mesh our model. Basically, when the geometry is imported to our environment, once you do generate mesh, it will create a default mesh for your structure. I have changed my units to millimeter, so if I click on mesh, go to element size, at the moment it's default. I will change it to, let's make a large mesh size. I'm going to change it to 10 millimeter, which is fairly large for this dimension. Right click on mesh and update. By looking at it, I'm not happy with it. It's the mesh are fairly large. The aspect ratio could be relatively high as well. I will have another video later talking about the mesh quality. So instead of 10, I would put 3 millimeter. That's fairly small. What I know is that most of these sections won't be under a certain boundary condition. So even if I have large mesh size as general dimension, say 5 millimeter, I could insert localized sizing to these surfaces. Select all of these surfaces. There we go. You need to hold Control key when you're selecting, otherwise it will not select all these surfaces. So while clicking on these surfaces, make sure that you have held the control button down. There you go. I apply these surfaces. Now for mesh size, I apply 2 millimeter and update mesh. By doing that, it will allocate small mesh sizes locally. At the moment, because of small chamfers in these edges, it gives me a bit small mesh sizes and a bit not normal mesh dimensions locally. Again, as I mentioned, I will talk about these things in my other video. For now, let's say that we're not worried about the mesh quality, and we just want to learn how to solve a structure. So I proceed with applying the boundary conditions. Before I apply boundary conditions, let's have some understanding about how Allen key is operated. We use Allen key by inserting one side into the bolt and holding the other side by finger, or sometimes we use other tools to hold it. I'm going to assume this setup in this picture, so I'm going to assume that the shorter side is inserted in into the bolt, and we hold the other arm and twist Allen key. By holding the mouse pointer on static structural, right click, insert and apply force. Now I'm going to assume that I will attempt twisting this Allen key by pushing this end, as you can see, clockwise towards Z direction. I am going to use a symbolic force. I'm going to use 1 Newton. It doesn't matter at the moment because we're not analyzing it accurately. We just want to learn how to apply the load. So in the table created for force, first it needs the geometry that the force needs to be applied. Although we hold most of these surfaces, but the fact is that our effective load is applied to the opposite side, so say to these two faces. By pushing the Allen key, we apply the effective load on the opposite side to rotate Allen key clockwise. So I select those two surfaces. In the tab called defined by, it's currently vector. I will change it to component, and as I mentioned before, our force is going to be in Z direction. So in Z section I will apply 1 Newton. So we did apply the force. However, we know that the other side of this Allen key is inserted into a bolt. It is an individual judgment. It depends on how people are going to apply the boundary conditions here. I'm going to assume that this Allen key is held on its edges rather than on the surfaces, because I personally believe that when you twist it, the edges they interface with the edges of the bolt, the slot, and those edges carry the highest reaction force. For that reason, I'm going to assume worst case scenario, and I will apply my boundary conditions on those edges. Again, by right clicking on static structure, I will go to displacement, I will select these edges by holding the control button again. Okay, we've selected all the edges. Press on apply. I'm going to assume that these edges cannot move on X direction and Z direction, because technically these edges can be inserted forward and backward, so they're free to move in Y direction. For that reason, I will apply 0 and 0 on X and Z. However, another boundary condition that we need to apply is somehow to restrain this end of the Allen key in Y direction, and that is going to be this surface. This surface in Allen key is technically free on X and Z direction, but it cannot move on Y direction because it's constrained. Well, we have set up the model. It's ready to be analyzed. I repeat that in this video I'm not gonna care about the element quality, mesh quality. We're just trying to understand how to apply boundary conditions and how to analyze a model. But mesh quality is a crucial part of preparing the model, and we will talk about it in a separate video. Before I analyze this, there's a point I need to highlight. I'm sure you've noticed that I've created some surfaces, individual surfaces at both ends of this Allen key. When I downloaded its file, those surfaces didn't exist, and I knew that it's going to be difficult for me to specify a certain length to apply my boundary conditions if the surfaces are continuous. So for that reason, and again referring back to the reality, as you could see, not all these surfaces are engaged within our boundary conditions, whether force or displacement. For that reason, I edited my geometry file. It is simple procedure to do. It depends on what software you use. All you have to do is just split these surfaces at both sides. Using Inventor, we could use I would choose offset this plane as the reference. Cut these surfaces. I will show you. I will say in one slide how to do it at distance minus 10 millimeter. Then in split, I will choose this plane as the tool. When it comes to faces, I will hold Control button again, and I will select all the surfaces. Okay. By pressing on OK, now you have these surfaces individually cut and ready to be used. And you could do the same thing in the other side as well. I'm not gonna do it now. I have also opened the raw file. As you could see, if I was to apply boundary conditions, I couldn't choose the edges only. So that was the reason I've made those amendments and prepared my geometry, amended it when it was necessary. Okay, once the model is ready and we are sure that we have applied correct boundary conditions, go to Solution section, right click, and then insert the information that you need after analysis done. I'm going to need total deformation for my analysis. I'm also going to need von Mises stress. After you inserted these, just press on solve. Depending on your computer processing power, it could take a while to solve the model. After the model is solved, it will show you the result. Now I've clicked on total deformation. As you can see, the blue color indicates 0. As you go higher on the colors, the red one is the maximum deformation. It is total deformation, so it doesn't show the direction of motion at the moment. If you press on play, it will show you the gradual deformation and how it's propagated. By clicking on equivalent stress, you will see the result for von Mises stress. As we expected, we have the highest stress or stress concentration on the edges where the boundary condition ended. You could insert different results such as directional deformation. So when you insert directional deformation, you could go on orientation and choose the direction that you want. Say I want Z direction in this occasion. You don't need to solve the model again, you simply right click and evaluate the result. Well, that's mainly it. I hope it's been useful.